Here's our beautiful D-Latch. I rebuilt it to make it a little neater, and there's a video that shows that. It's pretty boring, but if you want to see it, you can. And what we're going to do now is turn it into a D flip-flop, apparently. And it's a little crazy to me because, so we started here with a set reset latch, which is one set of NOT AND gates. And then we added these other NOT AND gates and an inverter and stuff to make it into a data latch. And then now what we're going to do is duplicate the entire thing again. Just seems sort of nuts. The benefit here seems to be something to do with edge detection. We have our enable signal, and he tells the memory cell when to listen to our input. This is our input, this is our enable. So right now we have a 0, and so if we synchronize it, it stays 0. But if we turn on a 1 and we synchronize it, it turns on. So we tell him when to listen to this value. And this is either 1 or 0, obviously, and this is when to listen, 1 or 0. When we put in data, so for example, the button's not pressed, and then we press the button, what we want is to press enable, and the output goes up, right? The LED turns on, right? When we press enable, we can see that in this line here, the output turns on. It stores at that memory, that bit. But in this example, if we release our data before we release the enable, then it will actually move the output back down to 0, which is not very good design. We really want this to be a cycle-based system. So in this cycle, we set the bit to 0. In this cycle, we set the bit to 1. In this cycle, we set the bit to 0. We don't really want to have, we turn on the bit and then we turn off the bit in one cycle. And what happened there is, since I removed the data pin first, or the button, my enable is still down. So it's actually going to, I guess, latch, which is why it's called a latch. It's going to latch onto that value. Really, what we want to happen, we only want the bit value, the memory cell, to take the data one time per cycle. In other words, when we click to synchronize, right now if our data is 0, this is going to be the enable, right? Now it's called a clock in the flip-flop, but if we hit the enable, we can see that the data, the output stays 0 when it synchronizes. And even though the data goes to 1, right, before the clock comes down, the memory cell doesn't register that. He's only looking at the very beginning, which is what's called the edge, at the rising edge of the signal. In our case right now, we have to release enable before the bit value on the data of what we want to store it properly. So if we want to store 1, we have to press enable and then release enable before data. If we release data first, then it latches onto a 0 in this cycle. And if this happens very quickly, it turns into a problem and a bug, and I guess you'd have to debug it and figure out your timing. But with this improved system, we don't need to worry about that. When we set the data, then the clock, the enable, right? We can just keep calling it enable. When it goes up, then only at that moment when it's going up is it going to look at data. I still can't believe it takes so many components to do that. So what's going to happen is our data is going to get input from the top NOT AND gate of this new monster over here. And our enable is actually going to go through 2 inverters, which I don't really understand why. But we're basically going to get an inverter signal, a signal coming in, and then we're going to map it. It's going to go in parallel to these guys. I guess we should give it a shot. Seems insane for 1 bit. Cool. Let's do it. So what do we do first? These 2 are identical. So I guess the thing to do is just to duplicate this entirely right here. Just boop, do everything again. And then we worry about our outputs after that. And we'll probably use wires because this is getting very long. Like the distances are getting far. So let's do that. Whew. All right, let's give it a shot. All right, so we're gonna make another SR latch essentially. So I'm gonna just put them right here and the next one right here in series. We need our power. Power goes in, ground goes in. So these ones are gonna be flipped around. We'll put them right there and the other one right in series. Okay, so in this case, the collectors are going to be right next to each other, which helps a lot with taking the output. All right, so we have our power. So now what we have to do is connect the outputs, which are going to be in parallel with each collector. So this collector is going to output to this base, and this collector is going to output to this base. I'm going to use 1K resistors. I have them lying around, so hopefully that works. All right, and then let's see if the other one can go right on top of that. This collector going to this base and this collector going to this base. So now what we need to do is basically put our connections in for the outside transistors, which is going to be our buttons, I guess. We should probably test it as an SR latch first and then test it as a data latch. So I'm going to put in some resistors to bridge the gap. Now we can put in our buttons and test this out. So button 1 goes in, button 2 goes in. We need to power up our buttons. I'm just going to use a 1K temporarily. All right. And now what we need is our output so we can see if it's actually working. So let's put in our LED. All right. Oh wait, wrong spot. Okay, let's give that a shot. I used a 10K by accident to power up the LED. So I'm going to take that out, plug up power, and I'll put in a 1K so it shines brighter. So this works as an SR latch with no AND gates. It's inverted, but it works. It's working as designed. So now what we can do is basically add the other side over here of what we need and go from there. So we basically have to duplicate this here, another set of not AND gates with an inverter on the side. In this case, we had an inverter, I think, over here. No, we have the inverter right here. So I'm going to add not AND gates and then go from there. We know that the bases are going to take a signal from the collectors. So the collectors have to line up with these two bases, essentially, the power sources of each one. So for example, on this other one, we have our inputs going into the bases, and they're in line with the collectors of these two outside transistors. So we can do the same thing here. Let me make sure they're facing the right way. So this one, the first one is facing away from us, we could say. All right, so let's do that. It goes in there, and this goes in series. Now we need to give it some power here. 10K should be fine. And then the other side, do the same thing. So we're gonna put this one, the collector, in line. And we have a problem. We're gonna run out of space, unfortunately. Let me move this over. And then we could put our connection back. Okay, cool. Yeah, could have been a lot worse there. All right, so now what we need to do is we have our two not AND gates. I need to give this one power, so let's put another 10K in. Okay. I really could have put these emitters together like I did on this one. These emitters line up with ground, and I only need one ground connection going in. I forgot to do that here, so I might just jump them with a little tiny turquoise guy. Yeah, this would have helped to save one row of space if I would have done it like that, but this works. So we have our second set of not AND gates, and I think they're configured properly. We have our ground, and we have our ground here, and we have our power going in, power being transferred across when there's no path to ground. And we know that the outside transistors, right, this one and this one, they're going to get the inputs from the actual buttons, from the data button. We still need to have our data button over here, and it's going to go into here and invert into this one. So it's essentially the same thing. So we really are duplicating this. So yeah, we need to turn this into a full D-Latch. So let's continue doing that. So we have our data button here. It needs to go into the two outside transistors. So this one and this one. This one is going to be through an inverter. So we need to make room for an inverter right here. So let's build a very simple inverter. 10K connection should be fine. And that should go into a transistor. The collector will ground. Okay. And then our output will just be like another 10K. And this will go into the bottom transistor. So maybe what I'll do is I'll take the output to this row right next to it. And then we can hopefully connect where this resistor is going over to this guy. That's the idea. So I don't know what cable that will be. All right, blue cable seems to do it pretty well. So we have our inverter going on this resistor to the blue cable to the outside transistor. And this button is just sitting on his side. What is up? I don't know where he's from. Oh, he's the other D-Latches data button. He wants to take part. So now we need to just connect our data to this inverter and to this inside the outside transistor's base. So like right here, perhaps. So let's move this guy a little better in position so we can connect both to the inverter, which is this pin right here. I guess I should really trim these guys. Maybe I'll do that. All right, so we have output of the inverter going to this blue cable through the resistor, and then we have the input right here. So now we just need to connect our button to the inverter and to the inside transistor. All right, I'm going to put a 1K, just because I have it handy, into the first inverter, into that outside base. So the button is going to go both through this resistor into this base and also into the inverter, which will then go on the blue cable to the outside transistor. And now what we need to do is have our, what do we need to do? We need to have our enable, which goes into the inside transistors. So I guess I'll just put the enable, again, running low on space here. Maybe I'll put the enable, I think I'm definitely gonna have to use some longer cables here. I think I'll put the enable out here and I'll give it some power. And then I'm just gonna use some long cables just so we can test this rapidly. So we have handy on us, we have a purple and we have a blue. So I'm just gonna put them into their separate inside bases. So the inside bases, you can't really see it too well, but they have these cables going in there and they're just connected to the button of the enable that's getting power from the resistor. So I'm gonna plug this in and see. I'm getting a feeling I forgot something, but let's try it out. Okay, I just realized that my data button does not have any power going to it, so that's definitely an issue. So let's put a 10K or something like that in there. Okay, so I think this works. So we can set it and then we can reset it. Set it. It's a little finicky. Oh, this came out. So we can reset it. We can set it, reset, set, reset. And then on this one, we can reset, set. Sorry, it's blurry. I know it's blurry. Reset, set. So we have two separate, the button came out. Man, I feel like I'm working with a glass sculpture that could just break at any moment. Definitely, I am not very good at laying this out properly. So we can set it, reset. And on this side, we can set and reset. Okay, so very messy, but now we have two data latches. And the key now to make something new, so we have this done here, right? We have this guy and we have this guy. These are buttons for us currently, and these are buttons for us currently. But now what we need to do is connect this guy's output to the input. So that means that instead of this data button being a button, it's actually going to be the output of this. So that's interesting. So this button is going to be removed, and this input is going to be drawn from this LED's output, essentially. So I guess what I'll do is I'll add the resistor that was into the button as a connection right here. And then this will be our data input for this side, this first data latch. And it will come from this point right here. So let's take out this LED. Let's add another cable. And I guess maybe make it, at this point, I really just need to use long cables, I think, to test it. So in parallel, we have our output. And then, so we have successfully, I think, put this guy into the old data button input. And now what we need to do is worry about the clock. So the clock used to be a button, which went to both, so that's fine. Now it needs to go into, this is a bit confusing. So we have our, I guess our button here, we could say. It says clock, it's our enable button, essentially. It needs to go through an inverter and then into this guy, and then through another inverter, and then it can act as our old button. So our old button right now just goes directly into the 2 transistors, which would be the equivalent of this, right? We have our button and it just goes into these 2 transistors. But now what we're going to do is we're going to connect a cable to it that goes through an inverter. So it depends on which way we want to start this. I guess we want to start over here with our actual input, and then we can invert it and put it into this outside guy's enable, which is this. These cables right here is his enable. So we have our button, and it needs to go basically into this part right here. Also through an inverter into this guy. Man, that's a lot of connections. All right, well, let's try it. So these cables will stay. This button will be removed. And I guess the enable can still stay down here. So we put the enable in there. Then we know it needs to go through 2 inverters. So first it goes through an inverter before it reaches this guy right here. So that's pretty easy. Okay, so let's do that. So we have to do like a 10K or something. Okay, and then we need a transistor. And then we need to ground that transistor. Okay, and then the button is going to go into this. Okay, so we have the enable button going into that transistor. And then after that, into the inverter, we have the enable button going into the inverter. And then from the inverter's output, we're going to, in parallel, connect it to our old enable, which is where these cables are coming from, and also through another inverter to the enable of the opposite gate. So we have our 1 inverter so far. So we have the enable button goes into this inverter, and then we need to take in parallel from the output position, which is basically in parallel with the collector. So this is our inverter here, and in this parallel line is where the 2 inputs are going to come from. So we know 1 is going to go just directly over here into the outside enable, and then we need 1 to go all the way over here to what this button is doing as the secondary. What I might do from now is take out this button, and then the resistor that was powering the button, I'll just put it right here as our resistance into this circuit. And then we'll place the input from our enable right here, the one that's going through that second inverter. All right, so our output is from this first inverter, and it's going to go right here, just a little quick jump. And then it's going to go into another inverter and then go across. So let's do that. Okay, so that is this connection here. We just took from the inverter and we put it into the enable of the outside data latch. And then now what we're going to do is we're going to build another inverter, and then that's going to go into our original enable. So okay, so we need another inverter. At least we're getting really good at making the logic gates, I think. It's probably the main benefit to doing all of this. So I need another, maybe a 10K, 1K, 10K, I don't know, 10K I guess. And we'll just build it right over here. So we have input that goes into a transistor. And then we ground it. Okay, add the ground. Now what we can do is just put in the enable output from the inverter into the secondary inverter. And I'm going to use another 1K because I used a 1K on this first connection, right? This one right here. So I'm going to use the same 1K just to add this equal current to make sure it's split properly. And then this inverter, the second inverter's output, is going to go to that original enable signal from the first data latch that we had. So I'm going to just put in parallel with the collector. And then we just need 1 cable, I think, to finish this. So we have maybe this yellow cable. We'll go all the way over here. to this original enable signal. Okay. Well, it's very messy, but I think it's set up. I guess I should try it before anything. And I think magically it's working. So if I put my data down and I tap my enable, we see that it works just as before, and then I'll release my data. So the key thing here is that would work as before, but right now we want to see if I release my data before my enable, will it hold the signal? So I'm going to hold data, I'm going to press in enable, I'm going to release data, and we can see that data is still being stored. So we can see that when we put the enable down and we tap data, nothing happens because it already tried to read the value the first time we press enable. But if we hold data and we tap enable, then it works. If we hold data and tap and hold enable and release data, then we can see that it still holds value. So it's no longer latching onto the state of data as we hold down enable. It's only latching onto it or grabbing it when we first press the enable button. So it doesn't really matter how many times we click or unclick data when the enable is down. It only looked at the value once. So I think this works, and it's really incredibly messy. So we can see how we can't really build these from scratch unless we perhaps print them on proper boards. But it's really interesting to see how many transistors we have on here. So again, what's happening here is we have our data and we have our enable, which is really the clock in this case, but I'll call it enable. And then we have Q. And the key is, it doesn't really matter what we do with the enable signal when the enable is high. All that matters is if we click enable, then at that moment, Q is going to get essentially an alert, right? At this moment, he is going to be told, hey, you need to check for the data. So he's going to look at data and he's going to say, oh, data is high. So he goes high. And then he's going to stay high. Let's say the enable stays on. Well, even if data just goes up and down during this point, it doesn't matter at all to the output. He's not looking at this guy right now. So he could be doing cartwheels and he doesn't really care. So he's going forward. And then let's say we let go of our enable. Again, he doesn't care about that. So he keeps on going. And then we press our enable again. And at this moment, again, we have a rising edge. So this guy gets an alert and he says, oh, I got to check again. So he looks at data. And at this point, he sees that data, I guess we need to decide what it is. Let's say it's low. So at this moment in time, he looks now at data because of the rising edge and he sees that it's low, so he goes low. So it's only at this rising edge, when we first click the button, does he peek at data's value. Does he ask data, hey, what are you at this second? Doesn't matter any other time in between. Doesn't matter how long enable stays high. Of course, doesn't matter how long enable stays low. All that matters is that rising edge. And the falling edge does not count. So this is not what we want. That's not what he's looking for. He's looking for the rising edge. So as enable, if enable goes up and down, up and down, up and down, and our data let's see, does some weird stuff, then our output, and we can do it. So data, and this is our enable. Let's say Q. So Q is going to, right, we might hide data, to be honest. And then we might even hide the enable. So Q is just moving along, doesn't care about anything. I mean, I guess we need to start him at a low signal, just to start. So he's moving along, and at this point in time, he sees that there's a rising edge. So he peeks at data, and at that moment, data is low. So Q continues to be low. As he watches the enable, and the enable is still high, but he doesn't care about that. And then enable drops, he still doesn't care about that. And then only when we reach the next rising edge does he peek again at data. And we can see that data now seems to be high. at that very moment. So he goes high. And then he stays high. He stays high, stays high, stays high. Falling edge, he doesn't care about that. Then he gets to another rising edge. And at this point now, he peaks again. And we can see that in line with this, data is actually high. It had just gone high, but nobody cares. He's high now. So he stays high until the next. So that's falling edge, he doesn't care about the falling edge. Then we get to the next rising edge. And we peak again, and we see that data is low now. So we drop low at this moment, in line with the rising edge. And then we continue, and then there's no more rising edges, so he just stays low, right? Let's say there's no more. So really, you know, we didn't see too much of all of these up and downs. All we did was peak, right? We peaked here, we peaked here, we peaked, and peak as in P-E-E-K, not a mountain peak, right? We looked right here, we checked what data is at that moment. Right here, we checked what data is. Right here, we checked what data is. And right here. So the main benefit to this is, I guess, when you design systems, it's just much more precise to know that you're only checking at that very, very moment, and you're not carrying at any other point in between. So this was, what are these again? This is a D flip-flop, and it's very complicated. How many transistors are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 20 transistors to get 1 bit. It's quite expensive. I hope this was helpful. I know it's probably really hard to track like what I'm doing because of all of this craziness, but it's just interesting to see that we started with this SR-Latch, right? This was number 1. And then we added this other guy here who is the data latch. And he was number 2. And we're gaining functionality, right? Here we have 2 separate buttons to set and reset. So it's very sort of archaic. And then we added this other section, and now we have a dynamic input, and we just tell it when to listen to that input. And he's always listening as long as the enable is on or high. And then what we've added now is a whole nother D-Latch with a clock input. So this is another D-Latch. And this was number 3. And what we've done now is made it so that just when the enable is down, or in this case the enable is out here, I guess, just when the clock or the enable is high, I shouldn't have said down, when it's high or being pressed, only at the first moment does this guy turn on. And it has to do here with these inverters, and I don't really understand why we're inverting once and then inverting twice. Why can't we take it direct and then just invert once? But I guess I'll learn about that as I continue going. It's just really interesting to have this. So this is a data flip-flop. We can put in data, and it only listens on that rising edge of the clock. So I hope this is helpful, and I'll be moving on to the next one.